In this lecture video, we're going to introduce the idea of a probability distribution. A probability distribution is a description that gives the probability for each value of the random variable, which we refer to as x, and is often expressed in a graph, table, or formula format. The probability for each value of the random variable we notate as p of x. There are two things that must be true in order for a description to be a probability distribution. It must be that the sum of all of the probabilities is exactly 1, or very close to it if we're including rounding. It also must be true that the probability for each individual value of x is between 0 and 1 inclusive. Let's start by creating a probability distribution. In this example, the random variable is the number of children assigned female in the birth of 3 children. Our random variable x in this case is the number of children assigned female, and we need to determine the probability for each value that this x can take on. If there are 3 children, our options are 0, 1, 2, or 3 of those children being assigned female. Let's start by creating the sample space. I'm going to use a capital N to notate that a child is not assigned female. And I'll use a capital F to notate that a child is assigned female. Notice that there's only one option for all 3 children not being assigned female. There are 3 ways, however, that one child could be assigned female while the other 2 are not. There are also 3 ways where 2 of the children could be assigned female while 1 is not. And there's exactly 1 way that all 3 children could be assigned female. Now that we have our sample space, we can tell that there are 8 different options, and we can calculate the probability for each value of x. Since there's only 1 way to not have any children assigned female, the probability of that happening is 1 in 8, or 0.125. Since there are 3 ways to have 1 of 3 children assigned female, the probability of that happening is 3 in 8, or 0.375. There's also 3 ways to have 2 of the children assigned female, so we have the same probability, 3 divided by 8, or 0.375. And last, there's 1 way to have all 3 children assigned female, so the probability is 1 divided by 8, or 0.125. Notice that if we were to add up all of these probabilities, we would end up with 8 divided by 8, or exactly 1. If we are including all possibilities, then the total probability should add up to 1. In other words, we are certain that one of these events will occur, and we have not left anything out. Let's look at a different example. This time we're going to create a probability distribution where the random variable is the number of 2s rolled when rolling 2 dice. If we're rolling 2 dice, we have 3 options. We could have neither of the 2 dice land on 2. We could have 1 die land on 2 while the other does not, or we could have both dice land on 2. Let's calculate the probability for each of these scenarios. The probability of having neither of the dice land on 2s, or having no 2s, is the probability of the first die not landing on 2 times the probability of the second die not landing on 2. Since there are 6 options on a 6-sided die, the probability of the first die not landing on 2 is 5 divided by 6. And the probability of the second die not landing on 2 is also 5 divided by 6. And using the multiplication property, we can multiply these 2 values together and get 25 over 36, or 0.6944. Now let's calculate the probability of having 1 die land on 2. Notice that there are 2 different ways that this can happen, and we need to add those 2 probabilities together. We need the probability of the first die landing on 2 and the second die not landing on 2. And we need the probability of the first die not landing on 2, while the second one does. The probability of the first die landing on a 2 is 1 divided by 6. And the probability of the second die not landing on 2 is 5 divided by 6. In the same way, the probability of the first die not landing on 2 is 5 divided by 6, and the probability of the second die landing on 2 is 1 divided by 6. Putting this into our calculators, we have 0.1389 plus 0.1389 for a total probability of 0.2778. Finally, let's calculate the probability of both dice landing on 2s. That's the probability of the first die landing on 2, 1 divided by 6, times the second die landing on 2, another 1 divided by 6. And multiplying these together, we have a probability of 0.0278. One way to double check that we did this correctly is to add up all the probabilities. Make sure that they add up to exactly 1. If you get anything other than 1, then you know you've made a mistake somewhere along the way. In this next example, we are actually given a probability distribution, and you can add up those probabilities to make sure they add up to 1. Also notice that each individual probability is between 0 and 1 inclusive. In this situation, X represents the number of televisions in a household in the United States. We're first going to find the probability of a home in the United States with exactly 4 television sets. It's important to notice the word exactly, because that's exactly what P of 4 means. It's the probability of having exactly 4 televisions, not at least 4 or 4 or more. Looking at our probability distribution, we can see that P of 4 is equal to 0.16. So there's a 16% chance that a randomly selected home would have exactly 4 television sets. Now let's calculate the probability of finding a home that has less than 3 television sets. Notice the language less than 3. That means we want to include the options of having 0, 1, or 2 television sets. The probability of X being less than 3 is equal to the probability of 0 plus the probability of 1 plus the probability of 2. And looking at our probability distribution, we find that this is 0.02 plus 0.15 plus 0.29 for a sum total of 0.46. So there's a 46% chance that a randomly selected home would have 0, 1, or 2 television sets. Finally, in part C, let's find the probability of finding a home that has more than 4 television sets. That is, we want the probability of X being greater than 4. Notice that that's only one option. That's the probability of X equaling 5. And looking at our probability distribution, we find that the probability of X equaling 5, or a home having exactly 5 televisions, is 0.12. Recall the range rule of thumb, which says that significantly low values or unusually low values are those that are 2 standard deviations below the mean, or mu minus 2 sigma or lower. Significantly high values or unusually high values are 2 standard deviations above the mean, or mu plus 2 times sigma or higher. Any values between these are considered not significant, or they are called usual. In terms of probability, we define significant results slightly different. If we're looking at X successes among N trials, it's considered significantly high when the probability of X or more successes is less than or equal to 0.05. That is, the probability of X or more is less than or equal to 0.05, or less than or equal to 5%. We also consider X successes in N trials to be significantly low when the probability of that value for X or fewer successes is less than or equal to 0.05. That is, the probability of X or less is less than or equal to 0.05, or less than or equal to 5%. We're going to return to our TV example, but before we do, I want to point out one more thing. The rare event rule states that if under a given assumption the probability of a particular outcome occurs significantly less or significantly more than what we would expect with that assumption, then we can conclude that our original assumption is probably not correct. For example, suppose we're assuming that we have a fair coin, but we have some unexpected outcome, such as 992 heads in 1,000 tosses of the coin. The conclusion that we can make in this case is that our original assumption that the coin was fair was probably not correct. This is probably not a fair coin if we got these significant results. Returning to our probability distribution for the number of televisions in a household in the United States, let's first determine if 5 television sets is an unusually high number of television sets to have in a given household. In order to determine if 5 is unusually high, we need to find the probability of 5 or more. If this probability is less than or equal to 5% or 0.05, then it will be unusually high. This is the probability of having 5 television sets in the house, or 0.12. And since this number is greater than 0.05, we say that this is not significantly high, or not unusually high. Now let's determine if one television set is unusually low. To do that, we need to find the probability of 1 or less and see if that value is less than or equal to 5%. To find the probability of 1 or less, we need to take the probability of 0 and the probability of 1 and add those together. That's 0.02 plus 0.15, or 0.17. And since this value is greater than 0.05, this is not considered unusually low. Now let's determine if 0 television sets is an unusually low number. To find that, we need to calculate the probability of 0 or less, which is obviously just the probability of having no television sets. Looking at the probability distribution, we know that this probability is equal to 0.02. This time we have a value that is less than or equal to 0.05. So this is significant. We find that 0 is an unusually low number of television sets. The final thing that we'll look at in this lecture video is a probability histogram. You can probably figure out exactly what a probability histogram is given what you know about probability and histograms. But let's go ahead and create a probability histogram using this data. Our horizontal axis in this case will be our x values, and our vertical axis, or the height of the bars, will represent probabilities. Our x values are 0, 1, 2, and 3. Since our highest probability is 0.5, I will label the vertical axis accordingly. When x is 0, the corresponding probability is 0.3. So I'll start by constructing a bar with height of 0.3. The probability of x being 1 is 0.5. So I'll next create a bar with a height of 0.5. And we can continue in this way to finish our probability histogram. That concludes this lecture video where we introduced the idea of a probability distribution.